First of all, I would like to thank the organizers for giving me the opportunity to give this talk. This is my joint work with Konstantin Vorobyov. The title is a little bit different from that we have in abstracts. I'll speak of infinity norm minimization problems for nowhere zero eigenvectors of the block graph of Steiner triple systems. The outline is as follows. I give some introduction basic definitions, and then I consider the main problem for the first eigenvalue, then the second eigenvalue, and then I give some results on completely regular codes in the block graphs of Steiner triple systems, which are somehow related to these minimization problems. So throughout the talk, I denote by n choose k the Curie Gaussian binomial coefficient. And I denote the Grassmann graph as j, q, and k. This graph has k subspaces of fq to the n as vertices, and its edges are pairs of subspaces meeting in a k-1 subspace. I also include the Johnson graph in this series. This is the graph with vertices being k subsets of n element set, which is usually elements from 1 to n. And edges are pairs of subsets meeting in a k-1 subset. So several properties hold simultaneously for Grassmann graphs and Johnson graphs. So sometimes it is convenient to use this notation when we denote J1 and K as a Johnson graph J and K. So Curie Steiner triple system is a collection of three subspaces, which are called blocks of the fq to the n, such that any two subspace is a subspace of exactly one block. It is a generalization of the classic definition of Steiner triple systems, when we have sets instead of spaces. The order of Curie Steiner triple system is the dimension n of the ambient space, which is not the same as the number of points for Q at least 2. So when I refer to points of Steiner triple system, I mean the points of corresponding projective space. So if we consider a Steiner triple system S, we can construct the block intersection graph, which is denoted by gamma S, with vertices that are the blocks of S, and edges are pairs of subspaces meeting in a one subspace. So when we have Q equal to 1, we have the block intersection graph of classical Steiner triple systems, and we have sets instead of spaces in the definition. It is well known that this graph is strongly regular. Well, for the classic Steiner triple system, for Curie generalization, the situation is more, the explanation is more or less the same. As for existence of Steiner triple systems up to the order, we have the following. Steiner triple system in the classical sense, order n, exists if and only if its order is either 1 or 3 via modulo 6. A very recent result by Kivash, Sach, and Sony that actually the Curie generalizations of Steiner triple systems do exist for all orders that fulfill necessary integer conditions, starting with some order. So the proof is probabilistic, and so far we have the only kind of explicit construction for generalization of Steiner triple systems. It's a two-ary Steiner triple system of order 13 constructed by several authors in 2014. As an infinity norm of a real valued vector, I mean the maximum of the absolute values of the elements of this vector. A vector is called nowhere zero if all of its elements are non-zeros. And it's called integer if elements are integers. So I skip the definition of theta eigenvector. So in general, one might consider the following problem. Find the minimum of the infinity norm plus one of vectors that run through all non-where zero integer theta I eigenvectors of a distance regular graph gamma. So we denote this optimal value by mi gamma. I is the i's eigenvalue. Theta I is the i's eigenvalue of gamma. We minimize the norm plus one on all nowhere zero integer eigenvectors corresponding to this eigenvalue. Okay, so all this norm is finite always for distance regular graph and for any eigenvalue. Okay, and we are particularly interested in case when this graph gamma is the block graph of Steiner triple system or Johnson graph or Riemann graph. Okay, some little bit explanation is needed here. We have plus one here due to previous studies. I introduce one more definition, which is related to so-called flows for Steiner triple system. So suppose we have the point block incidence matrix of Steiner triple system S, which we denote by WS, and then nowhere zero integer vector U is called infinity norm plus one flow for S if this vector belongs to the null space of the incidence matrix of Steiner triple system. And the main problem here, this concept was introduced by Akbari, Shaki, and Mofidi in 2011, and the main problem here is to minimize this flow to show that it could be chosen as small as possible for several series of Steiner triple systems. And the relation between these two problems is as follows. Actually, this any vector belonging to the null space of the incidence matrix of Steiner triple systems is just the second eigenvalue of the block graph of the Steiner triple system. Yes, so I guess there's no T here. No, yes, this is a misprint. WS multiplied by U here, sorry. So, so now we look at the problem of minimizing the infinity norm for nowhere zero integer eigenvectors of the block graphs of Steiner triple systems for the first eigenvalue. More details. We have the following theorem that actually says more about the relation between the first eigenspaces of the block graph and that of Grassmann graph. So WS, let WS as before be the point block incidence matrix of Curie-Steiner triple system S of order n, and let W denote the point block incidence matrix of so-called trivial design, which is formed by all subspaces, all three subspaces of FQ to the n. And we have the following. Let's consider the complete graph, which has n choose 1 vertices. And any first eigenvector of this graph would be described as follows. It's just any vector having sum of its elements equal to 0. And if we multiply this vector by the transpose incidence matrix on the left, we obtain the first eigenvector of the block graph of Steiner triple system S. And we can do this also if we replace the incidence matrix of S with the incidence matrix for Grassmann graph. And we also obtain the first eigenvector of the Grassmann graph. And actually, both are isomorphisms between the first eigenspaces of the complete graph and the block graph, and that of the complete graph and the Grassmann graph. And actually, we can say a little bit more. We can say that actually any eigenvector, any first eigenvector of the block graph is an extension. Sorry, can be extended to the first eigenvector of the Grassmann graph in a unique way. By an extension, I mean just adding some extra elements to the vector. This follows just from the property that the rows of WS are subsets of the rows of W. And well, and also the restriction of each first eigenvector of the Grassmann graph to the blocks of Steiner triple system S is also first eigenvector of S. So these properties, extension or embedding properties for eigenspaces of two different graphs, but related graphs, were studied by Vorobyov in 2013 for Johnson graphs and Hamming graphs. So for Johnson graphs, there is an embedding of their eigenspaces into that of Hamming graphs. So let's look at this theorem from the perspective of our main problem. We minimize the infinity norm plus 1 of among vectors that are nowhere zero integer and theta I eigenvectors of graph gamma. We look at our block graph of Steiner triple system S, And for the first eigenvalue, we can say the following: M1 gamma S is not greater than M1 JQ and 3. It follows from this statement of the theorem. Once we have nowhere zero integer first eigenvector of Grassmann graph, one might consider its restriction to the blocks of S. And it's also an eigenvector, and by the choice, this vector is also nowhere zero and integer. For the following bounds for our optimum in the Johnson graph, I mean, when Q is equal to 1 here, just ordinary Johnson graphs, if n is 0, and if n is even, then n1 J and 3 is 4. In other cases, the bounds, we have only upper bounds, and they are, well, quite rough. And 1 of J and 3 is not greater than 10 when n is 1 via modulo 4. As for the infinity norm in the block graph of Steiner triple system, in the traditional sense, we have the following. Let S be Steiner triple system of order n, where n is not less than 9. Then if n is 109 modulo 12, then M1 gamma S is not greater than 4. In other cases, it is not greater than 5. We have some, well, pretty good upper bounds in this case. I give some illustration for this bound. We have points and of our Steiner triple system, and we consider an auxiliary graph for points 2 and 3. We connect 2 points with an edge labeled by 2 or 3 if there is a triple ij and this label k in our Steiner triple system. So suppose we have triple 1, 2, 3 in our Steiner triple system S, then 1, 2 has well, they 1 and 2 are adjacent, and the edge is labeled by 3 because 1, 2 is completed by 3 to the to a triple Steiner triple system. The same goes for 1, 3, but with label 2. And as for remaining points, we have actually the graph being just a collection of even length cycles with 2 and 3 alternating labels inside each of the cycles. Okay, and according to this theorem, we have to take an eigenvector on the complete graph whose vertices are points. We take we can take the following eigenvector. We set -1 in this vertex, 2 in this vertex, -3 in this vertex. Among all even length cycles, we choose one specific cycle and put values 1 on the path with 3 vertices, and then we put the remaining values alternating, can -1, 1, -1, 1, and so on. For all remaining cycles, we do just alternating procedure. So -1, 1, -1, 1, and so on. So we see that the sum of all values on the complete graph, I mean sum of all values on the vertices, is just 0. We have moreover property for the eigenvector of the block graph of Steiner triple system, also having non-zero values. Moreover, all values among the vertices of the block graph are in not greater than from -3 to 4, and 0 is not one of them. So what we have here is actually, we have shown that there exists nowhere 0 integer first eigenvector of the block graph of any Steiner triple system. In its infinity norm is exactly 4 here, which amount 4 plus 1 to 5 upper bound for our optimum. Okay, so I move on to the second eigenvalue. Again, the problem here is to give a good upper bound for infinity norm of flows, or in our terms, to give upper bounds on infinity norm of nowhere 0 integer second eigenvectors of the block graph. And our result here is the following. We take any Asmus-Madsen Steiner triple system of order at least 99. Then any nowhere 0 integer second eigenvector will have infinity norm. The optimum will be not greater than 4. So as a kind of transition point for from these optimization problems to completely regular codes, I look at the following best case. We minimize our infinity norm plus 1 among all nowhere 0 integer theta I eigenvectors of graph gamma. And when this optimum is as small as possible, it is as small as possible when it is 2. It means that we actually are looking for eigenvector whose elements are just +1 or -1. In other words, we work with a specific completely regular code. It has covering radius 1, i's eigenvalue, and its complement has the same intersection array as the original code. So this topic is itself interesting because of from different point of views. It was actually already considered by Sergey and Dmitry when they had a talk at the previous AGT. Partially the interest in this in completely regular codes of the block graph of Steiner triple system is spurred by generalizations of Cameron-Libler line classes. In particular, the block graph of projective or Hamming Steiner triple system is just the Grassmann graph. I guess we have 2 here, not Q. And actually, among all block graphs, these are the only block graph when we have complete characterization of completely regular codes with covering radius 1 up to parameters. Sergey and Dmitry also considered the Feinstein triple systems, their block graphs. Actually, I don't know what is the current status of the problem, which is to enumerate completely regular codes in the block graph of the Steiner triple systems. Okay, I would like also to thank Dennis for giving the definitions of completely regular code, distance partition. Okay, so maybe we should give facts concerning eigenvalues. If we put our intersection array as elements of the three-diagonal matrix, look at the values, eigenvalues of this matrix. Those are necessary the eigenvalues of the graph in which we take completely regular code, which is known as Lloyd's theorem. Okay, and when we speak of a completely regular code with covering radius 1, we just have two alternatives for non-trivial eigenvalue. It's the first eigenvalue or the second eigenvalue. When we speak of completely regular codes in the block graphs, we have the following examples of completely regular codes in the block graphs of Steiner triple systems. So here and below, I mean only Steiner triple systems in classical sense. The series are following a point code which consists of all triples incident to a certain point. A large subsystem which consists of all triples belonging to a subsystem of maximum possible order, n minus 1 divided by 2, when n is the order of our Steiner triple system. And the union of a point and large subsystem if these two are blockwise disjoint. So as for the second eigenvalue, the following proposition holds: a collection of blocks is a completely the collection of blocks in the block graph of Steiner triple system is a completely regular code with covering radius 1, and the second eigenvalue, if and only if this collection is just one sub-design of our Steiner triple system. Okay, so for the first eigenvalue, we have the following computer result. The main hypothesis here is that starting from order 13, they are the only completely regular codes with covering radius 1, and the first eigenvalue, not the second, sorry. With the first eigenvalue are those three. For n equal to 9, we have some counterexamples, but still for n equal 13 and order 15, we have 80 Steiner triple isomorphism classes of Steiner triple systems of order 15, 2 of order 13, and this hypothesis is true for this. Okay, I give some conclusion. We studied the infinity norm for nowhere zero integer eigenvectors of the block graph of Steiner triple system and the Johnson graph. We showed that the flow or the infinity norm for nowhere zero integer second eigenvectors for Asmus-Madsen Steiner triple system is upper bounded by 5 when order is at least 99. And also we characterized all completely regular codes with covering radius 1 in the block graphs of Steiner triple systems for orders 13 and 15. This is it. Thank you.